December 11th, 2022. The Orion capsule crashes into the Pacific Ocean. The world celebrates a flawless mission. But behind closed doors, when NASA engineers inspected the bottom of the spacecraft, the celebration stopped. The heat shield was supposed to protect the astronauts. Instead, it was doing something impossible. The return of the Orion spacecraft to Earth on December 11, 2022, was a moment of technical triumph that simultaneously revealed the profound fragility of human engineering when confronted by the true depths of the cosmic ocean. As the spacecraft bobbed in the Pacific Ocean after its 25.5-day journey around the Moon, the visual evidence of its passage through the atmosphere told a story that differed significantly from the pristine success suggested by initial telemetry. The heat shield, intended to erode in a smooth and predictable manner, returned pitted, rugged, and missing significant chunks of its protective material, a phenomenon that has since sparked intense debate within the aerospace community. This unsettling discovery serves as a modern echo of the cosmic shore, described by Carl Sagan, reminding us that while we have waded ankle-deep into the shallows of space, the currents of the deep ocean are far more violent and unpredictable than our most advanced models predicted. The Artemis I mission was the first integrated test of the Space Launch System and the Orion spacecraft, a voyage covering 1.4 million miles designed to push human-rated technology to its absolute limit. But the physical state of the craft upon recovery suggests that the boundary between success and catastrophe is as thin as a single layer of ablative material, raising fundamental questions about our readiness to transition from uncrewed tests to the survival of human lives in the proving ground of deep space. Just as a mechanical watch measures the unraveling of the universe through the lens of entropy, as Professor Brian Cox often suggests, Orion sensors were designed to measure the fragility of biological systems in a galaxy that is otherwise meaningless without a conscious observer to witness it. The wrongness, identified by post-flight analysis, is not merely a technical glitch. It is a critical moment where humanity confronts the reality that our current models of deep spaceflight are significantly flawed, necessitating a radical reimagining of the safety margins required for the next generation of lunar and Martian explorers. To understand why the mission's conclusion felt inherently problematic to the engineers who inspected the scorched hull, one must first analyze the fundamental shift in architecture between the Apollo era and the Artemis program. Apollo was a sprint, a focused and relatively short-lived dash to the lunar surface. Artemis, however, is envisioned as a marathon, requiring a sustained presence far beyond the protective embrace of the Earth's magnetosphere. The Orion capsule is not merely a larger version of the Apollo command module. It is a more complex ecosystem designed to sustain life in an environment that is significantly more hostile than our previous forays into orbit. This transition from short-duration missions to the proving ground of deep space necessitated a change in physical dimensions and structural requirements that introduced new variables into the physics of reentry. Orion is designed to carry a crew of 4 for missions lasting up to 21 days solo, or significantly longer when docked with the Lunar Gateway. This increased volume and the associated thermal load necessitated a transition from the monolithic heat shields used in the 1960s to a segmented approach. While the Apollo heat shield was a single, continuous piece of Avcoat material, Orion's shield consists of 186 individual blocks of the same material bonded together. This design choice was a pragmatic response to the manufacturing limitations of modern aerospace engineering, yet it introduced thousands of potential fault lines where thermal gradients could behave unpredictably, a complexity that became evident only under the extreme stress of Mach 32 reentry. The architectural complexity of Orion is further illustrated by the comparative data between the two eras of lunar exploration. The Apollo command module had a diameter of 3.9 meters, whereas Orion measures 5.0 meters, representing a 30% increase in surface area that must contend with the thermal load of atmospheric entry. This increased surface area, combined with the segmented nature of the shield, means that the vehicle is subjected to stresses that no previous human-rated craft has endured. Engineers noted that the interaction between the individual Avcoat segments during the intense heat of reentry created micro-vibrations and gas accumulation points that were entirely absent in the monolithic Apollo design. We are essentially using modern materials in a configuration that fundamentally changes the thermodynamic behavior of the entire system. Furthermore, the duration of exposure has increased significantly. While Apollo missions lasted roughly 8 to 12 days, Artemis I spanned 25.5 days, exposing the spacecraft to prolonged radiation and thermal cycling that may have contributed to the degradation of the bonding materials between the heat shield blocks. This transition from a single unified structure to a mosaic of 186 blocks created a new set of variables in aerothermodynamics, where the margin of safety for the heat shield is now being questioned as being much thinner than previously believed. A primary highlight of the Artemis I mission was the first-ever skip-entry maneuver performed by a human-rated spacecraft, a technique that is often compared to skipping a stone across a pond. This maneuver is a high-stakes balancing act between gravity, atmospheric drag, and aerodynamic lift, facilitated by the capsule's lift-to-drag ratio, which typically falls between 0.25 and 0.27. During its return from the Moon, Orion approached the Earth at approximately 25,000 miles per hour, or Mach 32. Rather than diving directly into the atmosphere, which would have subjected the crew to a single, intense 8G deceleration event, the capsule performed an initial dip, used its aerodynamic lift to skip back out into a temporary suborbital arc, and then performed a final reentry for splashdown. This technique offers significant advantages, such as extending the capsule's range from the 1,725-mile limit of Apollo to 5,524 miles, allowing for a consistent splashdown location off the coast of San Diego regardless of the lunar departure geometry. However, the something is wrong aspect of this maneuver emerged from the thermal soak period between the two dips. During the skip, while the capsule was momentarily outside the atmosphere, the heat accumulated during the first dip was not dissipated into the vacuum. Instead, it migrated deeper into the Avcoat material. This thermal energy accumulation created a pressure cooker effect where gases generated within the material during the first dip became trapped as the surface cooled and charred, leading to the cracking and spallation that horrified NASA engineers upon recovery. The mystery of Avcoat spallation represents the most visible sign that something had gone fundamentally wrong with the Orion return profile. Upon inspection, NASA identified over 100 locations where the Avcoat material had experienced char loss, the shedding of large, unexpected chunks of the charred outer layer. This was not the smooth, predictable ablation that engineers had seen in simulations and previous tests. It was a rugged, uneven erosion that left deep cavities in the shield. Ablation is a critical thermodynamic process where the shield is designed to melt and vaporize, carrying heat away from the capsule through a process called pyrolysis. Under normal conditions, Avcoat forms a char layer that is supposed to be permeable, allowing the internal gases created by the heat to vent into space. However, the Artemis I investigation determined that the root cause of the spallation was a lack of permeability in the charred layer formed during the specific heating profile of a lunar return. Because the char was not porous enough, the internal gas pressure built up until the stress exceeded the material's strength, causing the outer layer to crack and pop off in fragments rather than eroding uniformly. Ironically, ground tests using arc jet facilities failed to capture this phenomenon because they used much higher heating rates, which allowed the material to form a more permeable char more quickly. This revelation suggests that safer or gentler reentry profiles might actually be more dangerous for the material's integrity, a paradox that challenges the entire library of material response data used to design modern spacecraft. Beyond the heat shield, a more insidious danger was discovered in the hardware used to separate the crew module from the service module. Post-flight examination revealed that the separation bolts had suffered unexpected melting and erosion during re-entry. These bolts are the structural links that hold the capsule to its propulsion and power source. They must be severed precisely before the crew module enters the atmosphere, but the remaining hardware on the capsule's exterior must survive the intense thermal wake. The wrongness here is twofold. First, the erosion of these bolts created gaps in the thermal protection system, allowing high-temperature plasma to snake into the internal structure of the capsule, potentially damaging sensitive electronics or compromising the pressure hull. Second, the thermal models used by NASA to predict the performance of these bolts failed significantly, as the actual heating encountered during the Mach 32 re-entry exceeded the design capability predicted by simulations. This anomaly points to a fundamental misunderstanding of the aerothermodynamic environment in the wake of a blunt body capsule. As the capsule pushes through the air, it creates a massive shock wave, but behind this wave, in the shadow of the capsule, is a region of recirculating, high-energy plasma. Mapping the heat flux in this recirculating zone is notoriously difficult, and the fact that the separation bolts melted suggests that the re-entry shadow is far more violent than current fluid dynamics models suggest, representing a potential single-point failure that could lead to vehicle breakup during a crewed mission. As Orion journeyed back to Earth, its brain also began to experience strange phenomena in the form of ghosts in deep space. Flight controllers observed numerous faults in the star tracker system, the optical instruments used to navigate by the stars. These trackers are essential for maintaining the capsule's orientation. Without them, the craft would lose its ability to point its heat shield correctly or communicate with Earth. The investigation revealed that these faults were caused by single-event upsets in the tracker's random access memory, triggered by high-energy particles like cosmic rays or solar protons flipping memory bits from a 0 to a 1. While Orion's main flight computers are rad-hardened, using silicon-on-insulator technology, the star trackers were commercial off-the-shelf components that proved more vulnerable to the deep space radiation environment, which is 30 times more intense than that of the International Space Station. This anomaly also highlighted a breakdown in engineering culture and communication. The star trackers had a feature where they set an error detection and correction bit whenever they successfully fixed a radiation-induced error. NASA's flight team, however, interpreted this bit as a sign of impending failure, leading to a state of high alert for a problem that was actually the system working as intended to self-correct. This miscommunication was due to several factors, including the European origin of the hardware and limited information exchange due to export controls, illustrating how technical complexity can lead to human misunderstanding during critical mission phases. Inside the cabin of Orion during Artemis, I were two silent passengers who experienced the return in a way no human ever has: Helga and Zohar. These were anthropomorphic phantoms, constructed of tissue-equivalent materials and fitted with over 12,000 radiation sensors, designed to measure the biological toll of deep space travel with a specific focus on the risks faced by female astronauts. The data they collected revealed the sheer variability and unpredictability of the radiation environment, showing a patchwork of exposure where the dose varied by a factor of 4 depending on where inside the capsule the sensor was placed. Most of the radiation was absorbed as the craft passed through the Van Allen belts, but a surprising discovery was that by simply rotating the spacecraft 90 degrees during the transit of these belts, the radiation dose was cut in half. While these results validated that the storm shelter under the seats can protect against acute radiation sickness, they also revealed that the long-term cancer risk remains high. The Matryoshka Astrorad radiation experiment demonstrated that the space between planets is not a vacuum but a radiation soup that we are only beginning to map, with galactic cosmic rays acting as high-Z particles that can tunnel through spacecraft and create secondary radiation showers even more dangerous than the original particles. The return journey through the Van Allen radiation belts also exposed technical anomalies in the spacecraft's power systems. These belts, populated by medium-energy protons and high-energy electrons trapped by the Earth's magnetic field, act as a natural barrier to human exploration. For Artemis I, the trajectory was designed to minimize the time spent in the most intense regions, yet even this rapid transit caused issues. The star tracker anomalies peaked during these passes, and the interaction between the belts and the spacecraft's own electrical fields remains a black box of physics. Orion uses a 120-volt DC power system to reduce weight, but this high voltage makes the electronics more susceptible to arcing in the plasma-rich environment of the belts. During Flight Day 19, 4 power conditioning components were switched open without command, an anomaly that engineers attribute to electrical interference or noise reaching the power unit box. While no major failures occurred, the noisy data from the power control unit suggests that the electrical heartbeat of the spacecraft was struggling against the invisible pressures of the Earth's magnetosphere, proving that returning home through the belts is not a simple reentry but a crossing of a turbulent electrical frontier. The failure of ground tests to replicate the Avcoat spallation is perhaps the most disturbing wrongness of the Orion return, revealing that our most advanced facilities cannot fully simulate the environment of a lunar return. The investigation found that the gentler heating of the skip entry allowed a non-permeable char to form, which trapped gases and caused the material to crack when external pressure was reduced. This suggests a fundamental flaw in the worst-case scenario testing philosophy, where engineers assumed that surviving the hottest conditions meant surviving all conditions. Artemis I proved that a middle-ground heating profile could trigger material failure modes that are absent in extreme heat, meaning the entire library of material response data used to design modern spacecraft may be biased toward extreme cases, leaving a blind spot in the moderate but deadly zones of reentry physics. This discrepancy highlights the limits of chemical propulsion and traditional shielding, especially when looking at the Mars roadblock. A voyage to Mars is not just a longer trip. It is a fundamentally different challenge where the mortality rate from radiation alone could be as high as 50%, according to Professor Luciano Ayas. The spallation risk at higher speeds and the long-term biological toll suggest that we may need to abandon the capsule and shield model for technologies like nuclear thermal propulsion or electromagnetic shielding that currently exist only on white bards. Finally, there is a human layer to the wrongness of the Orion return: the tension between engineering transparency and institutional image. Following the splashdown, NASA was initially silent about the extent of the heat shield damage, even as engineers identified cavities and unexpected variations in the Avcoat. This has raised alarms among veteran astronauts and engineers who compare the situation to the pre-Challenger and pre-Columbia eras where management hats took precedence over engineering hats. The decision to proceed with Artemis 2 using an identical heat shield, with only minor operational changes to the trajectory, is viewed by some as a gamble with human life. We perform these uncrewed test flights specifically to find failures, but when they are found, there is a systemic pressure to label them as understood rather than acknowledging fundamental design flaws. The return of Orion was supposed to provide certainty. Instead, it has ignited a debate about whether our culture of safety has become a culture of compliance. As Carl Sagan reminded us, the Earth is the only home we've ever known, and there is no hint that help will come from elsewhere to save us from ourselves. The charred and pitted surface of Orion is a physical manifestation of that reality, a reminder that venturing beyond our atmosphere requires a level of wisdom we have yet to fully master, and that the wrongness found in the machine is a gift of data that could prevent the next disaster if only we have the courage to listen to it.